Hey fellas, welcome back to the channel. And in today's video, we are going to discuss about introduction of computer. When most people hear the word computer, they automatically assume intelligence. They imagine something that thinks like a human, something that understands language, something that had decisions. But that assumption is not accurate. A computer does not understand meaning. It does not know what success is. It does not know what failure is. It does not even know what number are. All it understands are electrical signals, high voltage and low voltage, on and off, zeros and ones. That's it. So the first mindset shift you need to make is this. A computer is not smart. It is fast, it is precise, but it is not intelligent in the human sense. It simply follows instructions. If you give it correct instructions, you get correct results. If you give it wrong instructions, you get wrong results. The machine does not care. It executes exactly what it is told. Now let's build the idea from scratch. Imagine you are running a small factory. Customers bring raw materials. Workers inside the factory process those materials. Then finished products are sent out. This factory has three main areas: a receiving area, a processing area, and a shipping area. In some computing terms, these are called input, processing, and output. Input is anything that sends information into the system. When you press a key on a keyboard, that is input. When you click a mouse, that is input. When a temperature sensor detects heat and sends a signal to a controller, that is input. Even when your phone detects a fingerprint, that is also an input. Input is simply raw data entering the system. Now, once input enters the system, something must process it. That something is the CPU, the central processing unit. Think of the CPU as the manager of the factory, but not a creative manager, more like a strict rule following manager who reads instructions from a manual and performs them exactly as written. The CPU does not create instruction, it does not invent solution, it simply reads and executes. The CPU operates in a repeating pattern, like the fetch, decode, execute cycle. First, it fetches an instruction from memory. Then, it decodes the instruction to understand what operation is required. Finally, it executes the instruction. Then, it repeats the cycle: fetch, decode, execute, fetch, decode, execute over and over again. This cycle happens billion of times per second in modern system. Inside the CPU, there are smaller components that each play a role. One of the most important is the program counter. The program counter keeps track of where the CPU is in the list of instructions. Imagine reading a long novel without a bookmark. Every time you stop, you would lose your place. The program counter prevents that problem. It always points to the address of the next instruction that needs to be executed. After each instruction, it moves forward. Another critical part is the instruction decoder. Instructions are stored in binary form. The decoder translates these binary patterns into actions. It's like a translator that converts coded message into clear commands. Then we have the ALU, also known as Arithmetic Logic Unit. That is where actual calculation happens. If the instruction says add two numbers, the ALU perform addition. If the instruction say compare value, the ALU perform comparison. If the instructions say perform a logical AND operation, the ALU handles that. The ALU is like the workshop inside the factory where tools are used to shape materials. Registers are also located inside the CPU. They are extremely small storage spaces that hold temporary data. They are much faster than main memory. Think of them as small trays placed next to a worker. Instead of walking to the storage room every few seconds, the worker keeps frequently used tools within arm's reach. Registers serve the exact purpose. Now let's talk about memory. Memory is any place where data can be stored for later use. Memory has three important characteristics: capacity, organization, and access time. Capacity refers to how much information it can store. If you compare it to a warehouse, capacity is the size of the warehouse. Organization refers to how storage spaces structured inside the warehouse. For example, you might have 128 shelves and each shelf can hold 4 boxes. Access time refers to how quickly you can retrieve something from storage. A well organized warehouse with fast workers has low access time. A messy warehouse with slow workers has high access time. There are two main types of semiconductor memory: RAM and ROM. RAM is temporary memory, it holds data while the system is powered on. Once power is removed, everything stored in the RAM disappears. It is like writing on a whiteboard. When you erase it, the information is gone. RAM is used for active tasks like running programs or temporarily storing data for the CPU when the CPU is working on. SRAM is a type of RAM that is fast and does not require refreshing. However, it consumes power and is expensive. DRAM, on the other hand, is a type that is cheaper and can store more data, but it needs to be refreshed constantly to maintain stored information. Most main memory in computer is DRAM because it balances cost and performance. ROM, on the other hand, is permanent memory. It stores instructions that do not disappear when power is removed. For example, when you turn on your computer, it needs some basic instruction to start up. These instructions are stored in ROM. Type of ROM include mask ROM, PROM, EPROM, and EEPROM, and flash memory. Flash memory is widely used today in USB drive and solid state drive, also known as SSDs. Now consider how all these components communicate. The CPU, memory, and input and output devices are connected through buses. A bus is simply a communication pathway. There are three main types of buses. The address bus carries the location of data. The data bus carries the actual data. The control bus carries signal like read and write. If the CPU wants to read data from memory location 50, it places 50 on the address bus, activates the read signal on the control bus, and receives that data through the data bus. There are two major computer architecture: von Neumann and Harvard. In von Neumann architecture, The same bus is used for both instructions and data. This can create a bottleneck because instruction and data compete for the same pathway. In Harvard architecture, instruction and data use separate buses. This reduces competition and increase speed. Many microcontrollers use Harvard architecture because it improves efficiency in embedded system. But in computer, von Neumann architecture are used mostly. Now let's understand the difference between microprocessor and a microcontroller. The most important concept in which students get confused. A microprocessor contains only the CPU. It requires external memory, the input and output components. It is used in general purpose computer like desktops and laptops. A microcontroller, however, contains the CPU, RAM, ROM, and timers, and also include the input and output devices on a single chip. It is a complete system designed for specific tasks. Embedded systems are systems that use microcontrollers to perform dedicated functions. For example, a washing machine has a microcontroller that controls washing cycles. A car has multiple microcontrollers controlling airbags, braking system, and engine performance. A microwave has a microcontroller controlling heating, timing, and temperature. Similarly goes for an electric heater. These systems are not generally purpose computer. Mm, these systems are not general purpose computers. They are specialized machine performing defined tasks reliably. When engineers choose a microcontroller, they consider speed, memory size, number of input and output pins, power consumption, cost, and availability of development tools. In battery powered system, low power consumption is critical. In complex system, higher memory and processing speed may be necessary. At the most fundamental level, computing is about binary. Everything inside a computer is represented using zeros and ones. A high voltage might represent 1, a low voltage might represent 0. By combining millions of these simple signals, computer operations are performed. Images, videos, games, and applications are all built on the top of these binary foundations. So when you use a smartphone, play a game, or browse the internet, remember what is happening underneath. Instructions are being fetched from memory. The CPU is decoding them. The ALU is performing calculations. Data is moving through buses. Results are being stored and displayed. The process repeats continuously at incredible speed. There is no magic inside a computer. There are no tiny evils making decisions. There are only transistors switching on and off. But when organized properly, these simple switches create systems powerful enough to run cities, control airplanes, and simulate entire worlds. That is computing at its core. Simple rules repeated at high speed, structured in a disciplined way. Once you understand this foundation clearly, every advanced topic becomes easier to grasp because everything builds on this same basic structure. All right, let's talk about something that sounds scary, but it is actually very simple. Memory mapped I/O input output. When most students first hear this term, they immediately think it's some advanced hardware concept. It's not. It's just a clear design trick. So let's break it down from zero. First, Remember one important thing. The CPU only understands addresses. It does not see RAM, it does not see keyboard, and it does not see LED. It does not see sensors, it only sees number, addresses. Think of the CPU like a delivery rider. The driver does not care whether the address belongs to a house, a shop, or a hospital. He just delivers based on the number. Now, normally memory has addresses like 0, 1, 2, 3, all the way up to whatever size your memory supports. When the CPU wants data, it puts an address on the address bus, sends a read signal, and memory responds. Now, here's where memory mapped IO comes in. Instead of giving input and output devices their own separate communication system, we assign them normal memory address. Yes, that's it. We pretend input output devices are part of memory. Let's make this visual. Imagine your system has memory address from 0 to 255. Instead of using all 256 addresses of for RAM, we do this. Addresses from 0 to 199 is RAM, but addresses from 200 to 255 are input output devices. So when the CPU access address 210 to 10, it is not accessing RAM. It is communicating with an input output device. But here's the important part. The CPU does not know that from the CPU perspective, it is just reading or writing memory. That's the trick. Now, let's use a real world analogy. Imagine a city, houses are numbered from 1 to 200, but buildings are numbered from 201 to 220, are actually government offices. They still follow the same numbering system. The postman doesn't care. He just delivers based on the number. Same with the CPU. If it sends data to address 205, special hardware logic inside the system checks the address. If the address falls within the input output range, it activates the input output devices instead of RAM. The hardware logic is called address decoding. Now let's slow down and see what actually happens step by step when writing to an input output devices. Step 1. CPU puts the address on the address bus. Step 2. CPU puts the data on the data bus. Step 3. CPU activates the write signal on the control bus. Step 4. The address decoder checks the address range. Step 5. If the address belongs to an input output device, the device gets enabled. Step 6. The input output device stores or reacts to the data. For example, imagine an LED connected to your microcontroller. Let's say its control register is mapped to address 220. If you write 1 to address 220, the LED turns on. If you write 0 to address 220, the LED turns off. You are not calling a magical turn on the LED function. You are literally writing a memory address. That memory address is connected to hardware. Now let's compare with the something called peripheral input output. In peripheral input output, the input output devices have a completely separate address space. That means the CPU needs special instruction like in and out to talk to them. Then that make things slightly more complicated. In memory map IO, you do not need special instructions. You use the same load to store instruction that you use for memory. that makes programming easier and cleaner. Now let's talk about advantages. First advantage is that simpler CPU design, no special input output instruction needed. More flexibility, you can use all normal memory operation on input output devices. You can move data, compare value, use pointers. Everything works naturally. Now let's talk about some disadvantages. Because input output devices use part of the memory address space, you lose some memory capacity. If you have 256 address total and 56 are used for input output, you only have 200 left for RAM. That's the trade-off. Now there's something important for microcontroller students. If you ever programmed something like an AVR and written port E is equal to 0xFF, you might using memory mapped IO. Port B is the specific memory address. You are writing a value into that address, and that value directly controls hardware pins. That's powerful. Now let me simplify the entire concept into one line. Mapped IO mean IO devices are treated like memory by giving them memory address. That's it. No magic, no mystery. It's just smart address management. If you understand that the CPU only understands addresses, everything becomes logical. And once this clicks, embedded system become much more easier to understand. So now you know that the truth. Memory mapped IO is not some complicated hardware mystery. It's just a smart way of giving IO devices normal memory address so the CPU can talk to them like a regular memory. Once you understand that the CPU only sees addresses, everything becomes simple. If this finally made it click for you, then you are not memorizing anymore. You are actually understanding how system work, understand the code, and that's the difference between passing exam and becoming dangerous in engineering. If you found this useful, make sure you like the video, subscribe for more deep but simple explanations, and drop a comment telling me which topic you want breakdown. Let's build real understanding, not just notes. See you in the next one. Goodbye.